In this video, I will be exploring magnetic braking and levitation utilizing the inductance of large copper plates. These plates I picked up on eBay for a pretty reasonable price, along with some very strong neodymium magnets. Together they behave in strange ways. Copper is not magnetic, so they don't exactly attract each other, but at the same time this magnet doesn't seem to want to slip off very quickly. It drags across the plate slowly, like it's moving through a thick fluid. It's even more interesting if I drop the magnet on the plate. It slows down mid-air and gently floats to the surface. So if the copper is not magnetic, something else must be causing this. And many of you probably already know the answer has to do with electricity. When a magnetic field moves through copper and many other metals, it causes electrons to reorganize themselves and flow in a circular pattern perpendicular to the oncoming magnetic field. Of course, the electrons were perfectly happy being where they were before the magnet tried moving them around, and so they resist this movement by generating a temporary magnetic field of their own. There's no attraction or repulsion, just resistance to change. One way that we can prove this resistance is due to the flow of electricity is by replacing the copper plates with a copper coil. This coil of wire is not connected at the ends, and so it does not form a complete electrical circuit. If we tried to make electrons flow around this coil, they would have nowhere to go, and we can tell this is the case because when I drop a magnet through the center, there is no resistance. It falls through the coil as if it were not even there, no slowing down at all. If the resistance to movement we saw with the copper plate was an inherent property of copper, nothing to do with electricity, the magnet should still slow down, even with a disconnected circuit. When I do connect the two ends of the copper wire, now the magnet pauses as soon as it reaches the coil, and it takes a moment to make it all the way through. Electrons can now make a complete orbit around the coil in response to the oncoming magnetic field, and so the magnet slows down as its momentum is converted into electrical current. If I once again disconnect the coil and bridge the circuit with an LED, we can see a better indication of the electricity. The LED is very efficient, so powering it doesn't slow down the magnet quite as much as when the circuit was closed directly. This is a simplified model of how the majority of the world's electricity is generated. There are many different types of power plants, but most of them are just trying to figure out different ways to more efficiently move magnets through coils of wire. Now back to the copper plates, we can't so easily get electricity from these like we can from a coil, but the electrons are still flowing and cause very heavy resistance to a strong magnet. Because of this, we can do some interesting things like manually levitate a magnet above the surface. I'm doing this by holding a second magnet underneath the plate. It's not easy to make a magnet float in this way, but it is fun to practice. I found that using a very wide magnet on top and a smaller magnet underneath is the most controllable setup. I made a small stand to hold my copper plates out of wood and acrylic glass. The resistance to movement caused by the electrical inductance in the copper is the only reason this levitation is possible. On a surface without this property, a magnet will fly right off the side as soon as you try to lift it with a second magnet. Despite the resistance that we've seen to change, magnetic fields pass right through copper as if it were not even there, as we can see by how I'm able to rotate this small cube magnet from a long distance away, even with the copper plate separating the magnet in my hand. Replacing the disc magnet with this smaller cube in the earlier setup allows me to walk it across the surface like a little robot, and the motion damping provided by the copper gives me very precise control. Besides the generation of electricity, there are a few other practical applications for this sort of motion damping. High-speed trains and even some roller coasters use a magnetic braking system set up in a way very similar to this, with powerful magnets, usually electromagnets, elevated above a conductive surface. The magnets slow the vehicle down quickly without any surface-to-surface friction that causes damage in conventional braking systems between brake pads and rotors. My favorite tabletop demonstration of magnetic braking is to swing a magnet toward a chunk of copper like a wrecking ball. The magnet loses all of its momentum at the very last moment in a way that almost looks supernatural. It reminds me of a scene in the second Matrix movie where Neo stops bullets in midair. What's really happening is of course the same thing that has happened in my other examples. The magnet's momentum is slowed by opposing magnetic fields generated by the flow of electrons in the copper. And since the electrical energy isn't being collected by a circuit for any useful purpose, it dissipates into the lump of copper as heat. So the copper actually gets warmer every time I swing the magnet toward it, but by such a small amount that measuring the change would be very difficult.
All of the things that you've seen demonstrated in this video are described by two scientific principles: Faraday's law of induction and Lenz's law.